Good afternoon, class. Today we're going to go through some exercises working with the concept of encapsulation with C#. So at this point, hopefully you have gone ahead and accepted the assignment from GitHub Classroom, and you should be on your repository or go visit your repository page. We're going to want to take that project and we're going to clone that to our local machine, and that's what we're going to work on. Now, there are a couple different ways you can do this. You have probably gone and copied this URL before, then come into Visual Studio and told it you were going to start from a repository and pasted the repository into the dialog. I'm going to show you how to do it from the command line rather than doing it that way. And I like to do this because I really want you to get some practice working with the command line. So in Windows, that is CMD is the name of the program. If you're running on a Mac or a Linux system, it would be the terminal, but once you get into that, it's pretty much the same. Also on a Windows machine, you could instead choose to use PowerShell or something similar. So here we are at the command prompt, and I'd want to go to whatever drive I have this on and whatever directory I want to put my files into. So in this case, I'm just going to be using this ES400 folder on my D drive as my place of operations. And then the command for working with Git at the command line is git clone. To say I want to clone an existing repository, I'm just going to paste that repository name, or actually URL, in there. And it will go out to GitHub and grab and download and then unpack a copy of that into this directory. So if I come in and look at that drive and dive down into that folder, you can see we have our solution right there. If we double click that, it will open it in Visual Studio. Actually, it opened it in another one, so we will take a look at that. Okay, so that opens it in Visual Studio. Notice that in this case it started us on the Team Explorer. I want to switch to the Solution Explorer, and we also want to make sure that we are in the solution view, not the folder view, which it looks like we are. So here are 3 projects that we have declared here. And this is where we're actually going to start our discussion about encapsulation. So in C#, every project is its own encapsulated identity. So we have vector exercises here, which is a console app. You can see it has a program CS, and it's going to basically just execute and print out this hello vectors. We have vector math, which is actually a .NET standard library, and there's nothing declared in it, no files yet. Then we also have this vector math tests, which is a test project. So each one of these generates their own thing. A console app or a Windows Forms app or a Windows Presentation Foundation app create a binary file that we call an executable. So a file you can double click on and it will run in Windows, or a file whose name we can type at the command prompt and run it in Windows. A library, on the other hand, generates a binary file called a DLL, or a dynamic link library, which can be then used by other programs as a basis for how they're going to operate. And the test project, it kind of does its own thing, but it basically generates tests that we can run that are going to, in this case, work on this vector math library. And we have, if we look in there, it's already pre-populated. Of course, it's going to underline a lot of this stuff in red because it hasn't been written by us yet. So we couldn't actually run these tests. It won't compile as it currently stands. Let's take a look at our vector math project. So what we're going to do in this project is we are going to create a struct to represent a vector, a 3-element vector. So if we go in and we can add a new item, And I don't believe a struct is actually listed here, but what I would normally do is I will go ahead and pretend like I'm creating a class. We're going to call it a vector3. Now, in the text, we discussed a little bit about what a struct is. So struct, in a lot of ways, is it's a compound data type. So it holds multiple values within its structure, and it provides a name for those. So this is kind of a predecessor to a class. It's a similar concept, but it only represents the state, not the behavior. So instead of a class, we're going to do a public struct. And it does have access modifiers just like a class does. So we'll go ahead and declare a public double x, a public double y, and a public double z. So those are our three properties of this vector. The vector can have an x component, a y component, and a z component. And then we'll go ahead and create a constructor too. So we'll have a public vector3 double x, double y, and double z. Now, it is a little bit different. In other languages that do structs, often they won't have the concept of a constructor, but C# did include that in their conception of how structs work, but it does work a little bit differently than we're used to in terms of and in most languages, structs don't have a constructor, but in C# they can. And really what that constructor is doing is just assigning initial values. And if you do have a constructor, it has to assign all of the values for that particular object. So these should be commas. And there we go. So we would have to say x and assign it a value. We're going to use our little x. Y, we're going to set that to the little y, and z we'll set to the little z. So all we're doing is when we build this is we're immediately assigning whatever values in this parameter to this property, whatever values in this parameter to this property or field, and whatever values in this parameter to this field. And that is a vector. And notice we've declared it in the vector math namespace. So the full name of this structure is vectormath.vector3. Now if we go back to our test project and take a look at this test, notice that it does not recognize vector math or vector3. One of the things we need to do is we need to tell it that it can look to this vector math DLL that's being generated there as the source of that property. So if we'll go into the dependencies, we right click on that, and we're just going to add a project reference, and we're going to check the vector math project. So now this project will be accessible in our test project. And notice as soon as that gets applied, all of the squirrely underlines for all of the vector declarations go away. Now vector math is still underlined in red because we haven't defined that particular class yet. So we'll go back and do that here and add a new class. And this one will be a class, and we'll just call it vector math. We're going to use this class as a module, as we'd use a module in a different language. So we're going to actually set this as a static class with only static methods. And those methods will just basically be library functions for doing vector math operations. Go ahead and declare this public static and a class vector math. And inside of that, we'll want to define various types of operations that we could do with a vector library. For example, we might want to compute the magnitude of a vector. And any methods we declare inside a static class also need to be static methods. Return type, we're going to return a double because the magnitude is just a single value. And we'll take a vector3 as the argument, which is going to be the vector that we're going to compute the magnitude of. And the magnitude is simply the square root, so math.square root, square root of the squares of the x, the y, and the z components. So math.pow to get us a square. We'll do vector.x and take it to the second power. Then we'll add to that math.pow vector.y. We'll take that to the second power. And math.pow z to the second power. And that is all we need to do to compute the magnitude. Now if we go ahead and save that and pop back over to our vector math test, notice that where our magnitude happens to be, it's down here. Now vector math.magnitude is not being recognized. Let's double check we've got everything right in our vector math. Public static class, vector math, public static double, magnitude. So that should be showing up. We might actually have to build this class. So let's go ahead and take a look at that. So if we right click and click build. Now in Visual Studio last semester you probably mostly just click this run button up here, which compiles, builds, and then runs the executable that's produced. In this particular case, we are building just a single one of these projects, the vector math project, and it's a library, so we can't actually run it. You can't run a DLL because there's nothing for it to do. It's just there as a reference for other things. Notice that it succeeded, and if we go in and take a look at our folders, we want to go into the project folder and drill down into vector math. Notice here the bin folder. If we drill down into that, here's the debug folder because we were building it in as a debug mode, and then it tells us that it's a Net Standard 2.0 project, and inside of that notice we have this vector math.dll. So this is the big thing it actually builds for us. This is the DLL that gets used by other libraries. And now that we've built that DLL, this math test should be happy that the magnitude's now defined. But it's not, so we may have to go ahead and finish building the rest of our vector3 functionality to make that happy. So if we go back to our vector math library class, let's go ahead and add normalize. And when we normalize a vector, we should be getting back a vector. So we'll go ahead and set the return type as a vector, and we take a vector as the argument. So normalization just means we're going to reduce that vector to length 1. So it's going to still point in the same direction, but it's going to be only of length 1. And that is done by first calculating what the magnitude is. And we can just invoke this directly by magnitude because we're in the same class, or we could say vector math.magnitude in front of it, and we pass in our vector. So that gives us the magnitude, and then that's how long the vector actually is. To make the new vector that we're generating, the normalized vector, be of unit length 1, we have to divide each one of the components by that magnitude. So we'll go ahead and do a return. We'll create a new vector3, and inside of that we will take our old vector, x component, divide it by magnitude, and vector.y, and divide it by magnitude. And our third parameter, which is our z parameter, is going to be vector.z divided by magnitude. This, in effect, gives us a vector that is of unit length, or length 1, and it matches our expectation there. So that's magnitude, normalize. Some of the other operations we can do with a vector is add two vectors. And if we add two vectors, we definitely are going to have two vectors as parameters. And we want to return a new vector. And this vector is going to be the result of summing those two vectors. So how we add vectors, if you remember back from calculus, is we take the x components and add them together, the y components and add them together, and the z components and add them together. So we can say a.x plus b.x, that should be our new x component for our vector, and then a.y plus b.y, add those together, that would be our second y component for our new vector, and then a.z plus b.z will get us our third component. So that's addition. Subtraction is going to work very similarly, where we take two vectors as arguments and we're returning a vector. The only difference is now we subtract the second vector from the first vector. So it's ax minus bx, ay minus by, and az minus bz. And then we might look at multiplying. Now, multiplying with vectors, it gets a little interesting because we actually have three different forms of multiplication. We're going to tackle scalar multiplication first. So scalar multiplication means we take one vector and we multiply it by a scalar value, so a double. And we will just return a new vector. And we will basically multiply the x, y, and z components by that scalar value. So s times a dot x, s times a dot y, s times a dot z, and that's scalar multiplication. And let's go ahead and scale static vector 3. Let's do dot product. So the dot product is one of the other forms of multiplication we can do with a vector. And it takes two vectors again. So dot product. And we're going to return new vector 3. And the dot product is computed by multiplying each one of the components and adding them together. So actually the return value should be a double here, not a vector. So it is a dot x plus b dot x, sorry, a dot x times b dot x plus a dot y times b dot y plus a dot z plus our times b dot z. So let me go back. We multiply the three components and then sum all of those values, and we get a set value, and that is the dot product. And the last kind of multiplication we'll deal with is the one that does return a vector, and this is the cross product. And it's called the cross product because for each of the components of the new vector we're building, we're actually multiplying the other two components against each other and subtracting the results. So it forms kind of a cross pattern as we're actually carrying out the multiplication. So to get the x field of our new vector, we actually multiply the a dot y times the b dot z, and we subtract from that a dot z times b dot y. So you notice the x is not used in that particular term. For the next one, it would be a dot z times b dot x minus a dot x times b dot z. And then we have the last component, which would be a dot x again times b dot y minus a dot z, or sorry, a dot y times b dot x. And that would be the cross product. So that's all the forms of multiplication that we have available to us. So that gives us kind of the complete library that we're looking for. We'll go ahead and save that. And if we go ahead and build this, you notice we built without errors. We go take a look at our vector math test project and open that test that we were writing. So we have a little challenge here. Notice this namespace vector math, and then I also called the class vector math, which is why it's complaining for us. And so let's rename our namespace. That's an easy way of dealing with this. Let's call this vector lib, or vector library. And that will mean that in our test file now, we need to import vector library as the namespace. And that should take care of this issue. And the reason it's not is interesting. Vector math. Oh, because this is still in vector math. And the class is vector math. There we go. We do that. That should take care of things here. Notice they're no longer complaining. It all looks good. And the nice thing about having a good test project is now we can actually go to our tools and go ahead and run our tests. So if we go to, test menu, run all tests, that's going to pop open our Test Explorer window, which in my case is not docked, but it might show up here or over here if you've docked it. Notice that it goes ahead and explores and finds all of those tests we've written. And it's showing us that right now none of those have been run. If we go ahead and click the, it's running right now. You can see it's running a build process. So it's got to build not only the test project, but it goes back and rebuilds any dependency projects. Then it runs all the tests, and notice that they are all passing with flying colors, which means we have done everything correctly in laying out our library. So the first few assignments, we're going to give you these tests suites to run, but a little bit later in the course, we're going to start writing our own suite of tests. So you might want to go ahead and take a look at some of these, get familiar with the syntax. We're using actually the XUnit testing library. I believe previously you may have been using InUnit, which was its predecessor. XUnit was basically an attempt to rewrite InUnit from the ground up, incorporating a lot of the lessons that the developers had learned from building those various things. So now we have encapsulated in this DLL a library that we've written. We've checked its functionality with some testing. We think everything's working fine. So now it's time to do something interesting with that. So now we have this program where we're going to run some exercises, and we would like to use that vector library. Now notice when I do this, it underlines it in red and says, I don't know what vector library is. Are you missing a directive or simply reference? And that's because vector library is defined in this project, the vector math project. So until that project's made accessible, this project, vector exercise, just does not know about it. So again, to add that in, we have to add a project reference on the vector exercises, and we're going to add a reference to the vector math. That means that it should now be able to access that DLL that we created by compiling that vector math library. And that's going to get us able to actually access this vector library. And you'll notice that now it's no longer underlined in red, but it is grayed out because we're not actually using anything in it. So let's go ahead and just do a simple fun exercise. Let's say we create a new vector. And just make it 10, 10, 10. And maybe do another one for 5, 6. And then let's add those together. Yeah. Go ahead and save that as a new vector 3. And we'll do vector math.add A and B. And then we'll write the result of that out to the command line. And notice that right now the project that's bolded is vector math. So if we click this run button, it's going to try to build vector math, which is not going to work. In fact, if we tried it, it's going to give us an error telling us a library project cannot be run. So if you ever see this one, this is why it's throwing it up for you. There we see a project with the output type of class library cannot be started directly. What we'll want to do is right click on our vector exercises, and we're going to come down and set this as the startup project right there. Set as startup project. Notice now it is bold, and also the name of what we're running up here is changed. So if we run this again, now we're going to go ahead and run that. Notice too, I don't know if you caught that, but in the build menu right there, we started building it, and it is building first the vector exercises DLL that it needs to link into to actually do its own thing. And here's the console that printed out. Notice we have hello vectors, vector library dot vector 3. And that's because when we printed our vector in vector exercises or in program, notice we just printed the vector. So what happens when we do that, when we try to treat a struct as a string, is we end up invoking its ToString method, which is a little interesting because a struct in C# is actually implemented with an object, and it does have a ToString method, but it's a little bit different than an object. But if what we wanted was to actually see the values, we'd have to do something like a vector, or maybe we should say the vector. And we'll use mathematical notation here, so we'll do the angle brackets. And then we want to put c dot x, comma, c dot y, comma, c dot z. And of course we want to concatenate all of these together. And we can do that with the plus. So this is one of the ways, and probably a way that you have done string concatenation before. So that is one possible way of doing that. If we go ahead and run it, and I didn't make any errors, you should see our vector. And you notice it prints it out the vector 14, 15, and 16, which is 10 plus 4 is 14, 10 plus 5 is 15, 10 plus 6 is 16. So that's exactly like what we'd expect. Now, you probably remember Jorge telling you, for example, that we shouldn't use, actually not Jorge, probably Julie or possibly Josh, telling you that in C# string concatenation is a slightly more expensive operation. We should use a string builder instead. That's perfectly fine. If we wanted to use a string builder, let's go ahead and do that, but let's do that for vector math.subtract. So here we are assigning a new value to the variable c, which is going to be the result of doing the subtraction. And okay, let's go ahead and do a slightly different one. Let's do vector math.subtract. And let's do our string concatenation a little bit differently. So I'm going to use some new syntactic sugar that was added, I think it was around Visual Studio version 7, where we can just insert the values directly into the string. C.Z. And this is basically going to operate the same way this concatenation did. This is a little something we call syntactic sugar. It's where we create new syntax to make it easier to do something we could already do. And basically, if you put a $sign in front of your string, you're enabling it to do this, where anything in the curly braces inside that string is then interpreted and then concatenated into the string at that point. This is just a more succinct way of writing this line right here. But they operate exactly the same, but I want you to see both of them because you'll probably see both of them in practice, and you may find that you prefer this version because it's a little faster and easier to type. Sometimes, especially the concatenation, trying to remember if you need double quotes and where you need double quotes and remembering all the plus signs, gets pretty messy. So that can be a little more user-friendly. And if we go ahead and run this, notice that we print out our first vector, then our second vector. So we do 14, 15, 16, and then we do the result of subtracting. 10 minus 4 is 6, 10 minus 5 is 5, 10 minus 6 is 4. So those all look exactly like we expect. Now, one of the things we talked about in the text was the idea that each one of these structs in this case encapsulates state. So this is the state of vector A, vector B has state, vector C has state, and then we're also changing the state of C when we go in here and we reassign it to a new vector. We could tweak it a little bit more even before we get to that point. We'd say C.x and we want to set that maybe to 10. So previously, oops, not C.x, let's change A.x. And Let's make it a -10. So we're just going to basically invert our prior value there. So if we run this again, notice that now it's a -14. While the original vector was still 10, down here we changed that particular value, that particular field, a.x, to be a -10, and then when we run this addition, we're going to see that change. So this is really kind of the idea. Our code defines the behavior, the steps that we're executing define the behavior of the program, and then our variables actually represent the state of our program. And in this kind of module sort of design, we have gone ahead and created the behavior in this module vector math, and we've defined what our state looks like using this struct. Now the big idea behind object orientation was to bring those together so you'd create those in one class, which is what we're going to do next time. So last step here, let's go ahead and save this project, push it back up to our GitHub, and we can do that by first doing git add, and then we'd want to add each one of the files that we've added to the project or each one of the files that we've changed in the project, and that will stage them so that they'll be included in our next commit. A lot of the time we don't want to go through and do that one by one, so we'll do git add and then a space and a period. This means add everything in the working directory except the stuff excluded by the git ignore file. Oops, and I have to be in the actual project directory, which in this case was named vector module exercises. So then we do a git add to add everything, and a git commit. -a is a special flag that tells our commit that we want to add everything, not just the stuff that is brand new, but the stuff that maybe has just had some changes made to it. It basically means commit everything that is currently being tracked. Because we've added everything, we don't strictly have to do that every time. It really just depends on what's in our working directory. And the second flag I'm going to use is -m, which means I want to include the commit message. So every time git creates a commit, it will save the time the commit was made. It will give the commit a name, which it uses a hash for, which is just a string of characters that seem very random. They're not generated randomly, but they kind of look like that. And it's not very human readable. And then a message that describes what we did in the commit. So we want to give it a really good message here, like finished creating the vector math library. And go ahead and run that. If you don't do the -m and give it a message, it's going to instead open a text editor and ask you to type it there and save that. And depending on your system, that text editor could be Vim, it could be Nano, it could be Notepad++. So I find it a lot easier just to do from the command line. And notice that it has gone ahead and showed us that 6 files may had changes in those. So, for example, program.cs, we made changes to vector3 and vector math obviously had changes. We did make a change in vector math.test, and also the solution and the project have their own files associated with them. So those files changed as well. And then we had create mode for the 2 new files that we just added, vector3 and vector math. We'd make sure that we got everything by running a git status. This is good best practice when you're working with Git. Make sure you didn't miss any files that need to be committed, and notice that it tells us that we have nothing to commit. The working tree is clean. That means everything in the project has been committed to Git or is part of the list of things that it ignores. Now we want to push this to GitHub. We do that with git push. and then we need to tell it which remote repository we're pushing to, and since we cloned it from GitHub, the origin is going to be GitHub. So we'll say git push origin, so push to GitHub, and then we're going to tell it we want to push the master branch. And there you can see it goes through the process of compressing that data and sending it up to GitHub. If we go back and look at our GitHub page and refresh it here, now you'll notice that we have a commit that came in just 2 minutes ago that has all our information. But we have now committed and pushed that. And one of the things we're asking you to do this semester that you probably haven't done before is also to create a release once you've got your code to the finished form. And we'll call this assignment done. And we'll go ahead and click the publish release. And now if we go back to our vector module exercises, notice that we now have, should have a release. I may have forgotten to save something. Assignment done. No, I didn't give a version. So v.1.0.0, because we're using semantic versioning, and this is the first final release, so it's not a pre-release. So 1.0.0. If I go back later and realize I left something out or need to fix something, then I would name it v.1.0.1 to replace that. And we'll talk a little bit about semantic versioning here in a bit, but we'll go ahead and just publish that release. And that time it worked. So now we have assignment done. If we go back to our main page, notice that now we have one tag, which is for that release, and over here in the releases section, we have one release, which is the assignment done. So that's what we would ask you to turn in for your homework would be this URL, which takes us directly to your release page. That way we grab the version of code that you want us to grade. This also means that you can go back in and we'll reuse some of these projects in future assignments. So we might revisit this one. In fact, we definitely will. So you'll want to come back to this code, make some new changes up in your project, push those to GitHub, and create a new release for that next assignment. And that should wrap up our discussion of some of the encapsulation techniques that we see in C#. You can see we encapsulated the structure of 3 doubles for a vector 3 inside of a struct. We encapsulated all the related functionality for working with a vector or a group of vectors inside a public static class, vector math, which is basically a library or a module, and that all of that was encapsulated within a library project, which is then used by a separate project. And in fact, we could create as many projects as we wanted that would use this library. Like this vector library might be very useful if we were building video games and we needed a vector library to work with that, or if we were building 3D modeling kind of program, or if we're doing maybe some advanced mathematics. All of those different places we might want to reuse this vector math library without having to rewrite it. And that's one of the other great benefits of encapsulation, is it helps us actually set up our software in a way that becomes very reusable. So that's all for this go round. So we'll go ahead and wrap it up. Thank you for joining me.